Alright, hit the button. Yeah, right. Draft physics video. Another one on the interferometer, I think. Although the comments were sort of on the two-slit experiment, which is a little bit annoying. But, you know, maybe I'll deal with those first and then get on to other things. Observations. Further observations. No experimental data, but, well, some, but nothing recorded. Anyway, alright, so, now one of the comments is on the, the Casimir effect, whatever it's called, the Casimir effect, valid inside the slit. And I've sort of, it's not really. I think there's something to do with electrons and charge. But the Casimir effect is really about things that don't have charge on them, and they're brought really, really, really close to each other. And it just has to do with the fact that one will have to be negative and one will have to be positive when you bring two non-charged entities that are made of atoms in proximity to each other. Their charge will, likely have to accommodate the fact that the electrons don't like the electrons and the protons don't like the protons. So one of them has to go electrons sticking out, and one of them has, one of them has to go male, and one of them has to go female. It's just that kind of thing. So, but I don't think the two-slit experiment, the slits aren't nearly as close, and they're also part of a whole substance, so they're not going to be neutrally charged anyway. So that would be my explanation. So the hex guy says, let's say just hypothetically someone, again, there are two-slit videos, so really two-slit comments should go on the two-slit videos, I think. Someone manages to block one of the slit openings at a distance relatively large compared to the slit size. Well, I don't, even if it's the same distance as the slit size. Let's say you manage to block a slit without interfering with the experiment, quote unquote. Now if you get some double slit pattern, even when you blocked one of the beams, that would be considered definitive disproof of wave theory. Yes, sort of. I don't. The word definitive here is really, you got to be really careful in how you use it, and they have a million, catch-22 explanations for why things happen the way they happen. But yes, clearly, the two wave probability waves have to have access to the location for there to be destructive interference. And if you block one of the slits, then one of the wave packets can't get to the location where it's going to create the double negative, so to speak. And so, yes, you're correct. However, what it be if not too good, you get the single slit pattern exactly recovered as before, and the barrier is not close to the slit. If you get this single slit pattern, you're saying, and I don't know what an as before is, so it's pretty tricky to make a single slit next to a double slit and not call it the double slit. So I'm just saying the charge potentials are still going to be the same. So I suppose I would argue that you can't possibly get, you have to go by a measurement. So you have to say, if I take a measurement of the single slits in the double slit, and then I create a single slit of exactly the same dimension, and you get exactly that pattern, then you'd have kind of some sort of evidence that there clearly isn't any charge or communication across the barrier. That's all I would say, is the barrier somehow becomes irrelevant. But it all depends on how you're masking that second slit, because as I stated, you're creating a new piece of matter that you're putting in proximity to the experiment, which means if it has a charge, that charge is going to influence the other elements of the experiment. So, but yes, this is all theoretically, not bad, but this is the kind of stuff somebody with really precise instruments has to do. You can't, this is a little tricky for at-home experiment. Anyway, before the barrier, not close to the slit, would that count as evidence against? It just depends on how well the experiment's done. I suppose it would count as evidence against something other than a wave theory. But I'd have to think through the permutations of, again, how you actually accomplished taking the slit out of the experiment, because it's not that easy to take it out without mechanically interfering. Okay, that's enough. That's it. That was it for the, nothing brilliant in the comment section, unfortunately. All right, so yeah, lots of little things I thought of, but there was the key issue I guess I'll go over is this whole dust thing, creating diffraction gradients essentially. The whole point of the diffraction gradient, probably you've got to find a word for a half-silvered mirror for all of these obstructions that you put in an interferometer to create the noise that makes this whole thing possible. So I have to think of some way to describe that. Some better verbiage than diffraction gradient. But anyway, it has to be really close to the surface of the glass, which is really interesting. It can't be, I was thinking you could have it far away, and I thought, well, that'd make this really easy to explain if, so we'll go back to a drawing of the experiment. And while I'm drawing, I'll just re-emphasize here that, so I read the web page that I was linked to on the other thing, the rest of it, and their explanation is quite convoluted, and it does, again, it's a wave theory explanation, but it has to do with different photons interfering with each other. So it's like two photons have to hit the dust particle at the same time on like either sides, and that really isn't quantum mechanics. I mean, there's no, this is a big problem in their theory, is that in the single slit experiment, they did the experiment one photon at a time and found out you get the same results. So they came up with this idea that this function is somehow in one photon, and it creates two probability waves and two Huygenses. Okay, so you can either say it as probability waves. So let's understand that, yes, it's true that some scientists don't bother with Huygens, like Feynman, for example. I don't think I ever heard him say Huygens' name. Because Feynman just says, forget about causes. Let's just understand that you start with situation A, and you end with situation B, or C, and all we care about is probability B. So the only thing in between A and C is the probability B, and we don't care what causes the probability. So people who say, well, it's a probability wave, they can just be saying it's a probability circumstance, whatever. They can just make up any kind of rhetoric. And I don't think that's really doing physics. The whole idea is to explain why things, how they happen, not to just sit there and say they happen. I mean, that's sort of a cop-out, in my opinion. But let's understand, their theories all depend on a single photon having these powers. So explanations that start mixing photons and creating interference between different photons are really problematic. Because frankly, you can't have the double high. The idea of their circumstances is the bar gets twice as bright, and the light was essentially heading for the dark space. There really isn't light plus light equals dark. That is, the energy died. Now the energy went to the bars. I mean, the theory doesn't really state that the light comes out, and wherever the bars are, light went there, but it's invisible, and therefore energy got destroyed there. And so we're only seeing a percentage of the light, like 70% or 60% of the light that went through the slits. Only 70% of it gets to the target. I don't think anybody's arguing that happens. So you can't really use this idea that somehow a photon went somewhere the wrong frequency, and therefore it doesn't count as a photon anymore because it can't be seen as a frequency. The theory is it doesn't go there. So that was another problem here, is that they're arguing out of both theories. when it's convenient, they have individual different photons interfering with each other. And then when they have to, because of the experiments with just single photons, they say the single photon has the wave probability function, and it does all of it on its own. And so you can't have both ways. Somebody should be able to agree they can't really have it both ways. Alright, I didn't get the drawing done. Didn't think that was going to work, to tell you the truth. Alright, alright, so we're back analyzing the experiment, and I'll just show you what I observed. Messing around. So I attempted to put the gradient, the dirty surface here. Okay, I probably should mark that with dots or something. So this is the dirty surface. So just take the light. Don't even worry about, I mean, I could have done a straight line, I didn't bother, but I mean, so you're just taking, the light hits, you get the reflection, it goes through the dirty surface, hits then it goes to the mirrored surface, and then goes back through the dirty surface, or, as I attempted to do, project it over here. So, and you get no pattern. So, if the dirty surface is over here, no pattern. If I put the dirty surface, like a little film, right next to the glass, very close, or right on it, pattern. And if I move the dirty surface, in this case a diffraction gradient, if I move it just a little bit, I get huge amounts of those of the going ins and going outs of the pattern. So the pattern does that, looks like it's getting bigger. It doesn't really get bigger, but it looks like it's coming out from the inside, and then it goes into the middle. So it has that forward and reverse look to it. And so any movement in this film creates a ton of that cycling. So that confirms the fact that this is about distances. Alright, so anyway, so this is cancelled in the sense that the distance isn't, you can't do it this way. And I'll try to attempt to describe the reasons why this doesn't work. And it has to do with this diffraction thing. So you really do have to follow the photons through the whole experiment to really get this, because it gets really complicated. The stuff I didn't think of. All right, so I guess we'll just do a straight line. I don't know if we need to make it complicated. So you send light into a see, the trick is the half-silvered mirrors are usually only glass on one side, and it's mirror on the other side, but no glass. Alright, so that's another part of this to understand. So let's just say that was half-silvered. So what you have to think about is the light that goes through, and just pretend the light's coming at an angle, just for the sake of whatever, the sake of something. Alright, so the light comes in, and there's a it is sort of interesting to consider what would happen for the light that's reflecting. Sorry, I mean, I'm going to end up thinking while I'm doing it. Yeah, that's curious. I was just thinking about the fact if the glass is on this surface, there'd almost be a double likelihood of reflection, because this surface of the glass is also going to reflect the light, as I've demonstrated. So, yeah, that's a problem. Anyway, I'm just trying to get to this part here, so I'll just pretend I haven't gone astray. Now, what you have to understand is the light that goes through is going to have, there's going to be two types. There's the initial laser beam, so it's this round beam of little rays, little straight line rays, and then there's the light that's going to hit the crap on the edges. Hit the crap and get reflected, so it's gone light. It's light that's no longer in the picture. and then the other light is going to go close to the edge of one of the pieces of dust, so it's going to be diffracted. Alright, so now if the target is far away, that diffraction means it won't even hit the target. The light will head off in directions that won't even get anywhere near this target. Say this is the mirror, that's the target mirror. So it doesn't have any chance of being significant. That's why the diffraction gradient can't be very far away from the mirrored surface, is because it diffracts so much that you'll miss it entirely, and so it can't possibly be relevant. Alright, so anyway, but the trick is the light that goes straight through, that doesn't get diffracted much, or gets diffracted very little or not at all. That light went through a grid of openings. Okay, so it still has this configuration. That is, if you were to look at the beam now, it's not a round full beam. It's a beam with holes in it where the light got blocked. So it's a beam of it's like a Dalmatian or something. It's not a full beam of light. Now it has a nice shape still, but it has an image on it essentially. So that image is what's going to reflect off the mirror. Now I assume these mirrors are just silver, no glass. I haven't made sure. I should go to the website by LIGO and see if the one they suggest using has any glass in front of it. So they're just silver, a mirror with no glass. Because the glass is going to make a mess of things. But it doesn't mess up. If the light's going in straight, it doesn't mess it up. So this light is still straight, although it has a pattern on it. And so when it reflects off the pattern, I mean, even if there is a mirror, it's probably okay. And what comes back, okay, is going to be that same pattern. And the idea is that pattern is going to hit the same location, if you have it lined up right, that it left from, except it's going to have the amount of, see, this is where it gets so subtly complex, because even though this beam is still intact, it very slightly diverges with distance. So it's not being diffracted, it's not being wildly spread, it's just slightly diverging. So when the pattern comes back, it can't fit into the same holes it came through of dust, the spaces between the dust. So, but it's going to maximize the potential of hitting, because it's now a little bigger, because it's all diverged. So, this is probably the way to do it, is to draw it in red or something. Oh, okay, you couldn't see my little divergence lines, but yeah, you probably get by without them. So what's going to happen is when the light comes back through, it's going to be wider than the holes that it went through, thus guaranteeing, okay, essentially, a bunch of diffraction around those holes, one could argue. Again, this part is just speculation. I mean, because I think the likelihood of being able to line it up wouldn't be too high, but I don't know, maybe. But regardless, the point is the light's coming back. It has a pattern in it, and that's what's the key to creating the pattern. The rings are created when you go through the grating twice. So when you have the grating really close, let's see, I guess I should create a new piece of paper, I guess. So when you have so here's your glass, and then you have the mirrored surface, and then you have the dirty stuff on the top. So what's happening is the light goes in, gets diffracted by the dust, and it bends at funny angles, you know, somewhat funny, exaggerated angles. And some of the angles are really extreme. Okay, so you have to understand that some of the angles are really extreme. They're angles that can be anything on this, you know, this idea. So they can be anywhere from, you know, 10 degrees or something to, you know, 100 degrees. You know, so, and the wider, the longer they get more and more likely to create perpetual internal reflections at like the Brewster angle. So they'll just reflect right out the side of the glass. And some light just gets plainly transmitted out the side of the glass. I mean, always. You know, you hit the glass and some light comes straight out of the glass. So some light comes out of the glass at angles and some light comes out straight, even when it's not internally reflecting. I mean, it's just transmitted across the surface somehow. But anyway, that's a whole nother subject. Alright, so yeah, so you have these lots of angles, and that's what's creating the rings, is all these different angles that the light is coming off of and then reflecting out at. And the glass surface dictates whether it comes out or if it's light or dark, and the angles decide the location. Let's say within those, well, it's really the only bands that do a lot of changing are these interior ones. So these are the ones that you really have to deal with. They're the ones cycling. These don't change much at all, the ones on the outside. So anyway, but that's the trick is it goes in lots of angles and then it has to go back out through the same grid work. So now it gets rebent in all kinds of angles. So it's basically getting diverged twice. So diverging twice and hitting a piece of glass is the key to the pattern, I think. I think that's the only reasonable conclusion why it's this crap has to be so close to the surface. So anyway, so the way to get around this, I'm thinking, is to have the glass and then have the diffraction gradient. You shoot the light through it, then you bounce it off of something that's just silvered. So I have to have just a silvered mirror with no glass. And then it'll go through this pattern a second time, and you get a pattern. And that way, when you adjust this distance, you'll be adjusting the amount of divergence and therefore the angles of the reflections taking place inside this piece of glass. So that, I think, is the key to it. So I just have to come up with a piece of an aluminum might work, something that doesn't have glass in front of it, to use as a mirror, and then I might be able to get this to work as just a one-way street. So anyway, that's what I have observed. Let's see if there's anything else I wanted to add. I mean, the tricky part is just recognizing that there's two things happening to the light when it goes through this thing. The stuff that reflects off of this doesn't diverge, so all these are real honest reflections. The stuff that goes through diverges, and the stuff that goes through but doesn't go near one of the pieces of dust goes through straight, but it will have the pattern built into its whatever. The beam will have a pattern built into it, and that pattern is going to be reflected back. Right. So it's pretty complicated. Yeah. But so I thought, like I said, I have to find the real good demonstration of how this doesn't really have anything to do with the two legs and recombining the light. It just has to do with the one leg, you know, and the fact that that's what's creating the pattern and such. So I think that's, you know, the other thing I think it's worth mentioning, I suppose, is just in the sense of where does the wave function come from. So there's another thing, you know, people keep bringing up this wave function. It's a formula, and the formula doesn't, you know, doesn't have in it any overt waveness. Okay, you can call it a pattern formula. So they choose to say it's the wave math or the wave equation. Yeah, that's the word they use. The wave equation. It's not really a wave equation. It's a pattern equation. It describes patterns. So they've given it a name that really it doesn't have to have. It's describing making patterns. And so this is why all the rhetoric and everything is so prejudiced towards these wave explanations. So the probability, as I've argued, you know, even with the surface of glass and then with the surface of electrons, I think a fundamental thing that creates this idea of something out of phase is the idea that a fundamental principle in physics and in geometry is if you want to take a bunch of chaotic circles, all right, just in a field, chaotic little things, and you want to compress them to maximize how close you can get them, you know, especially if they have forces they're around them. But even without forces, the idea is that you do stagger them, you know, especially if they have a geometric shape like a square or triangle. Not a square wouldn't work, but obviously a triangle or something like that, where you fit them in a pattern, okay, that is essentially can be looked at and seen as a phase pattern. Okay, these are the downs these are in phase, and these are in phase. Alright, so that is starting to create, obviously, right? On, off, on, off, on, off, on, off, on, off. I mean, it's just such simple geometry that dictates you do something like that. That's how geometric objects fit together, is by taking them and putting them out of phase. So being out of phase is a fundamental element here. And so what I'm arguing is that the electrons on surfaces are probably doing a similar thing when they're under pressure. When there's extra pressure, they, you know, maximize their positions, take all the extra out so they can get as close as possible to each other, to spread, to dampen the force. And that's their hedge against it, is to get as close as they can. It's not to waste any space being, you know, having extra gaps, you know, bigger gaps than the standard gap. I don't know how else to explain it, but you're just taking as much space as possible out. And so I'd say that not only do electrons do it, but that atoms do it. And this is the source of the wave equation. This is because this is the fundamental part of the wave equation, is the fact that you have things in alignment or in phase. And so I'd argue that there's just a huge prejudice that everybody thinks, you know, you wouldn't call this a wave. It's a pattern. And you can make it look wavy. You know, I can draw little extras here, and I can even do this and say, look, it's a wave. It's not a wave. It's a geometric pattern that optimizes, I don't know, position or force. It maximizes a kind of efficiency of distance, and it's not having anything to do with waveness. And I'm just arguing that it's probably a fundamental feature of all of the subatomic geometry, that it's going to get into patterns like this that are out of phase, that create phase. Alright, so I think that's another important thing. I think that will be an important thing. Okay, if these videos are ever going to be remembered, that's going to be one of the things that is important, is that every time you see a pattern that has a reoccurring element, you don't call it a wave. Okay, it's just a pattern with a reoccurring element. Okay, it's not a wave. Something like that. Alright, anything else? Look at my notes. Yeah, so I'll try to do some experiments, but you know, I should be doing them now. So I can't sleep, but I'm not awake enough to want to do anything. Yeah, and I want to get to the ferrocell thing too, because all of this I think is really quite related. This whole optical thing that's going on here. Alright, yeah, that's probably enough. Yeah, I didn't articulate it very well, but I think I made the points, the major points that need to be made. And then again, the one I would really like to have an answer to is the people who are going to defend quantum mechanics. Do they think quantum mechanics says that different photons can have their wave function interfere with other photons? And if that's true, why is there no way to ever make a laser beam interfere with another laser beam? Or a light to bounce off of light? I mean, they probably have an answer for that, in the sense that well, you need to collapse its wave function before you can remake its wave function. So first you have to collapse it, and then you can have a new wave function. Some kind of crap like that. But anyway, do they think can they recognize that yes, there is a problem in quantum mechanics, in the sense that it seems, you know, that they had an answer for the two-slit by saying single photons carry this wave function, and now they're saying, you know, when it's convenient, no, but regular photons can interfere with each other. You know, they can photons can interfere with other photons. I mean, it can't be both ways, can it? Theoretically, sensibly, reasonably. I don't think it can reasonably be both ways. But anyway, till next time.